Okay. Cool, is it working?
Yes.
Where's the marker? Okay, so we're gonna go to this problem. The first thought, you have two parents, right? And they both are heterozygous. Okay, so we can do a couple things with this. First thing we do is draw the Punnett square. It's always the easiest way to get started. So big A, little a, big A, little a. And so the four possibilities are big A, big A, big A, little a, big A, little a. And over here we have, oh my goodness, I messed up on that one, please forgive me. Little a, and over here we have big A, little a. Did I get that right?
Shouldn't pay any attention
Yes.
to you.
Okay, please excuse my grandma. Cool. So if we just had this problem and we said, okay, they have a child, what is the probability the child is heterozygous for this gene? Well, that's pretty easy. We look at all the possibilities. So there are four possibilities from this pairing. Big A, little a, and two heterozygous. So there's four possibilities. And the number of ones that are heterozygous are 2. So the probability of having a heterozygous child is 2 out of 4, which is the same as 1/2. That you know how to do. This is simple. I just wanted to make sure we're good on that. Now, the problem here is that we have another piece of information, just one other piece of information. If we had more, that would be different. But we know the child has a big A first. We know they at least have one dominant allele, which means that we can eliminate this possibility. That's the only bit of information we have. We don't know if that big A came from this parent or this parent. All we know is that that they have one. So the only one we can eliminate on this board of possibilities is 2 little a's, because we know that's for sure a no. So then we go back and we do the same process.
You know you're bringing food over.
Erase that.
What time?
We have 2 possibilities that are heterozygous out of 3 total possibilities, because we've eliminated 1. Which means that with the information that the first one's a big A, that we know there's at least one dominant allele, there are 2 out of 3 total possibilities with this pairing that give the child a big A, little a. Okay, now that seems kind of wrong maybe, and I hope you can look at this and you'll be able to see, okay, well that seems right, and I hope the only thing you're thinking now is, but it doesn't make sense with everything else. So now we're going to go and look at the other possibility. I think this is what you keep thinking about. So, it's 2/3 if we know that the child is not A. If we can eliminate that, we know the answer is 2/3. Now, it's a different question if I say, we know that this parent, the dad, or this parent, I'm going to remove that here, we'll call that the mom, I guess. If we know that one of them, we know which gene they passed on, then it changes the probability again. So let's say we know that this one is an A. Well, that means we eliminate both of these options, because, well, we know that this is not in the game. Then we look, okay, well, how many are heterozygous? That's 1. How many are there total? 1, 2. 1/2 again. That's another case where there's 1/2 probability of the heterozygous. But it's from different information than what we had. Knowing that this parent specifically gave an A is different from knowing that just one of the parents gave an A. Because you see, normally we couldn't eliminate this box. Okay, let's go, I wonder if there's anything else I can do to help explain this a little bit more clearly. Yeah, that's the best I've got. Hopefully this helps. Message me if it doesn't. I think you can make comments on this, I'm not sure. Okay, you can stop the video.